In the last video I brought up that there's a decent amount of review that we need to do out of Chem 1 and Chem 2. And I wanted to remind you of a couple of very specific pieces. We need to remind ourselves of our SI units, our metric prefixes, conversion factors and how we use them efficiently and effectively, and also unitary analysis. Now, I really want us to pay attention to that third and fourth one because that's one where you probably have a decent background, but you may not be as polished at it as you need to be. Let's work toward that. So our SI units, that's going to be, well, if you're using the 8th edition of the textbook, the black version, that'll be table 1.1 and table 1.2 on page 14. And it'll give you a quick reminder. Now, we aren't going to spend much time talking about some of the ones that you see in the bottom table, or in fact on the bottom half of each table. So in table 1.1, we start bringing up units like candelas and radians and steradians. Yeah, we're not going to spend a lot of time using those. We're also probably not going to talk a lot about amperes, though that'll come up when we do our voltammetry section later in the course. In table 2, we're not going to spend a lot of time talking about forces in units of newtons. We're not going to be spending a ton of time talking about watts or coulombs or ohms or farads or volts. So make sure you're aware of them and you have some context. The key part is make sure you can find them in the text when you actually need to find them. So right there on page 14. Now when we get to our metric prefixes, there's obviously some that are a lot more common when it comes to the prefixes. So we aren't going to spend a lot of time talking about yada, zeta, exa, peta moles. Those are all 10 to the 15th up through 10 to the 24th. Those are such large numbers we rarely talk about something that size in chemistry unless we're talking about Avogadro's number itself, and even then we usually just leave it in raw numbers. Now, tera, giga, mega, kilo, those are really easy for us to recall thanks to the computer revolution. We know a kilobyte, we know a megabyte is 1,000 of those, or if we're saying in proper computer terminology, really 1024. We won't make the distinction. You know, if we have a giga, that's 1,000 megabytes. If we have a terabyte, that's 1,000 gigabytes. And we're probably even remembering that a petabyte would be if we had 1,000 of those terabyte hard drives. So we're pretty solid on the positive exponent side, especially when we remember hecto and deca. They times 10 to the second times 10 to the first. Then on the small side, here we actually will be using a lot of these units. We'll be using deci, centa, milli, micro, nano, and pico for sure. We'll bring up femtomoles once in a while, not really often, but occasionally. Femtomoles will come up because we're already down at 10 to the negative 15th. Pretty tiny number. Occasionally you'll hear about an attomolar measurement in the literature. Now that's bleeding edge of the field because we're talking about measuring 10 to the negative 18. Now keep in mind, Avogadro's number is 6.022 times 10 to the 23rd. So we're talking about something that's already on the scale, if we have a single atom, down at the yoctomolar level. So that'd be one atom in an entire mole. That's a pretty tiny number, and it's something we're very rarely going to be detecting. Single molecule fluorescence is possible to measure, but it's also an exotic and fairly bleeding edge part of the field. So once we get to attomolar, zeptomolar, and yoctomolar, we probably don't have to have those prefixes memorized super thoroughly, but we need to find them whenever we need them. And conversion factors, we'll need to use plenty of the conversion factors in table 1.4. We'll mostly be focused, of course, with volume, mass, pressure, energy, and temperature. We won't be bringing up force very often. Pressure comes up on occasion, but not a lot in analytical chemistry, at least not with the experiments we do in this course. Some of the energy units we won't be bringing up a lot, some we will, and we aren't going to really talk about horsepowers. Now, that said, all of those can act as our conversion factors, so we need to know how to use them. But the biggest thing I really want to remind us is that ideally, we should be able to chain these together in a long portion of a problem. And we'll take a look at an example of that in a second when we also consider our unitary analysis. Now, why do I bring that up? Here you see one of the spreadsheets that we're going to use for one of our first experiments in the semester. What we're going to be doing is we're going to be taking the mass of our empty glassware and then a certain amount of water inside of that glassware. And we're going to do our best to measure out exactly whatever amount we say. In this case, 10 milliliters, 25, 50. You can see that in each case, we have our mass jump up by about 10 grams, and we know water weighs about 1 gram per mole. So that seems about right. So if I added 10 milliliters, I sure expected that to jump up by 10 grams. The thing is, what does that actually tell us about the real volume that we've added based on that mass? Or at least another way of measuring that value. Well, to actually calculate that, what we need to do is we need to go from mass, and we need to subtract them to get this value. That's pretty straightforward. Then we need to use density. Actually, correction value Z is just the upside down version of density. So instead of grams per mil, this will be milliliters per gram. See that there's a little bit more than that milliliter in a gram. We can apply this and get this and get this, and whoa, you're already kind of rolling your eyes like, really? You're just going to point and say like this, like this, like this? How does that actually help us understand what our measurement is going to be? That's exactly my point. What we need to be doing is we need to be looking at the actual units. Now let's go ahead and take a quick glance at what that might look like for us. Suppose that I'll just toggle back and forth here. Let's say that I've done the subtraction and I know I have 9.9484 grams. I need to end up finding out how many milliliters that's supposed to be based on all the other pieces of information that I know. So I come back over here, and knowing the temperature, I would have gone to some table and I looked up this correction value. We'll skip that portion for now and just use this value, 1.0029. So it's going to be 1.0029. Remember that I said earlier this is the opposite setup of units compared to density. So instead of grams per milliliter, we're in milliliters per gram. I want to get my grams to cross cancel. You'll see me solve problems like this all the time. This is called a fence post. Each of these are going to be a fraction. Of course, we can always just write something in if we need to, if we're just doing a multiplication, because we don't have to have something on the bottom. That's divided by 1 with no unit. So we can just leave that box blank and not worry about it. In this case, we'll actually fill it out because it's way easier to keep track of our units. So what we do is we split up our fraction. We write in the top half of the fraction here. I'll put the 1 gram underneath it because remember what we're saying is we have this many milliliters per gram, per 1 gram. So then I just split off my next fraction by putting a bar across. Now I can cross cancel my units and I say, hey, my grams have cross canceled. I am currently in milliliters. That's exactly where I wanted to be. So life is good. I use this double stroke as an equal sign. Then I just go ahead and I multiply across the top. You can multiply across the bottom, write the top and bottom numbers here, and then divide it if you're worried about keeping track of your calculation throughout. Or if you're pretty comfortable with your calculator and you find that you're getting the right answer in the homework sets without flubbing on the calculator, then you can also just go this times that divided by that, and if this is longer, times that divided by that times that, etc. You go ahead and hit equals and Merry Christmas. You've got your value. That's how we do unitary analysis. That's keeping track of units throughout the problem. Conversion factors unitary analysis. I know that this is something you used like crazy in Chem 1, but it's often something people have gotten pretty weak at doing, so make sure that you have this repolished and ready to go.